this is Glenville Pecor. This is this study about Newton's first law. Basically, let's just start off with the basics of Newton's first law. An object at rest stays at rest. An object in motion will stay in motion at the same speed and in the same direction unless acted upon by unbalanced force. Well, remember, it's probably same velocity would be the word here. I should change that right now. Okay, cool, change it. Remember, speed is basically the absolute value of velocity. So you can say velocity. So basically, let's take this into experiments. So you get a ramp. So let's get a ramp. So we'll measure if you have a frictionless ramp and you drop a ball down it. So let's make that. Let's have a ramp. I don't know, because I don't want to ramp it sideways because that's just a little confusing. Pretend this ramp is 100% parallel. I give it, there's no friction. It's not a ramp now, it's just a platform. Try to make a perfect have a ball. I give it a push. Whoosh. If this ramp is frictionless, it will select, because of Newton's first law, an object will stay at rest. An object will stay in motion. Now, let's say an unbalanced force stops it. Let's say I put a wall right there. It's a wall. Pretend it stops immediately. Even though that probably won't happen in real life, but yeah, let's say somehow the ball stops immediately because of the wall. It goes like this, it stops because you stop it here with your hand. Let's say you stop here with your hand at the wall. Now, look at it. It's at rest. So if you put a ball here, and if it's basically it's at rest. So if I'm not going to touch it, see, I'm not touching it. It's not going to move. But pretend I touch it. I give it a push. Whoosh. Push, it goes this way. But it's going to keep on going the same direction until I stop it or something else stops it. Pretend I put my hand over here, right here, to stop it. See? There's an unbalanced force on it. Let's say I push it again. It's going to keep on doing here. Oh, no, it's going to hit the wall. Boom. It's going to change velocity because it hit the wall. So an unbalanced force, after it hits the wall, it's going to be constant because an unbalanced force affected. But after that, it's a single force pushing it back. So basically, that is what first law means. Now let's do a lab on it. But before I do the lab, let's just prove a common misconception. Let's say people think that, oh, if you throw the ball, it may speed up because it's rolling. Sorry, no, there may be a force on it because it's rolling. That's a common misconception that most people get. Alright, so since most people think the conversation, oh, let's draw a force diagram of the ball. Right after the instantaneous point, after the ball has been pushed. I'll show you what most people think, and I'll show you what's... So, drawing the vectors, you can tell the top is going to be normal force, the bottom is going to be in the middle is going to be right here, the middle's going to be, they think it's going to be force of hand on ball. But this is what most people think. Then of course there's always weight due to gravity. I'll also write force of earth on ball so people aren't confused. And for here, I'll just do force of floor on ball. And this is force of handball. This is what most people think. But actually they're wrong. Because after they're let go, they think, oh, there has to be something here because there's going to be a ball moving. Well, no. Because there's no such thing as force of hand on ball. Because after it's let go, this goes away. So this is what the diagram looks like. And if you don't know what a vector is, please look at my other video called How to Make Force Diagrams and Vectors. That'll be really helpful for this video. I'll leave a link in in the Google Drive document. It's gonna be a main document. So that's just a sub note. So basically, this is what the force diagram's gonna look like. Force of earth on ball. I'll put a backslash. Floor on ball versus earth ball, because there's only two things acting upon it. It's going to keep on moving and keep on moving and keep on moving. So that's how you're going to prove Newton's first law. Now let's actually go to this lab. Even though in my physics class we didn't do an experiment, but let's do a nice experiment. You're gonna have basically you're gonna do this. You can even do this at home. All you need is a playing card, on top of a plastic cup, a coin to put on top of the card, a sharp flick, hit the card. Basically, what you're gonna hit the card out from another coin, or pull it out real quick. The coin will drop into the cup. Explanation to this is basically what you're doing is the coin has inertia, meaning it really wants to stay in one place. So inertia is going to be with inertia. It's not going to move. If you move the card slowly, it isn't fast enough to overcome the force. If you flick it quickly, the coin stays in one place, then drops. Like basically flicking as in you pull the card as fast as you can. It drops in the cup. An object rests will remain at rest. Basically, this means is the coin's move. The coin, since it has equal, the vectors are equal to each other and they cancel out. So this is saying that total force or net force, whatever you like calling it, is equal to 0. So with that in mind, with the coin and the card, it's not going to move. So there we go. That's another simple way to show you it's real life. If you put a dent on a desk, it won't move because there's nothing moving. There's nothing touching it. So that's a good way to prove first law. Now, let me just draw a graph. There's really no need, honestly. Well, I'm going to draw you a graph of this ball. Actually, there is a need. Of this ball, when it moves, goes like this. Okay? I'm going to draw you a ball in first law. I'm going to draw you a graph. Here's what the position graph looks like. As you can tell, that the y graph would be meters and the x would be seconds. So meters time. So let's say you show here the ball moves 1 meter in 1 second. So you can say, oh, the ball's moving 1 meter per second. And since you push it, we're pushing on the ramp that has 0 friction, like we showed right here. The ramp has 0 friction. So with that in mind, I'm pushing. I'm not pushing it. So right here, as I let go, keeps on going, keeps on going. It's going to get farther and farther. But it's at the slope is constant, and it's going to be continue over, and it's going to be just constant slope. If you just move, if you show the next graph, if you look in the if you make this graph even larger and enlarge it, it's going to be a constant line. Since it's moving 1 meter per second, at 100 meters, it's going to be moving. It's going to 100 meters. It's going to be at 100 seconds. So there we go. Now let's look at the velocity graph. Now the velocity graph, basically, y is the meter second and x is seconds. So because velocity is meters seconds and x is in seconds. So basically, what you're saying is that look, see the slope is constant. That shows two things. One, that shows that the velocity is not changing, it's not increasing nor decreasing. Also, it proves that acceleration is 0 because of the slope is constant. But that's not important right now. So let's focus on the most important thing. Why is this like this? Well, because look at the slope. It's 0. Because the ball is moving at 1 meter per second due to the last graph I just showed you. Y is in meters per second. So it's always going to stay at 1 meter per second. But time will always change. So that is the graph of the ball on the ramp. So let's create a unique problem. Let's create a unique problem. I push the ball on this perfectly leveled ramp. The ramp is not to size because it is not perfect. There we go. It looks perfect now. I push it, and I push it with enough force to make the velocity equal 1 meter per second. So I push it. What will the velocity be at time equals 10? And what was the distance be? Well, let's go back to the graphs basically for this. This will be really well. Let's go back to the graph. I'm sorry, I misspoke. I meant to say when t equals to 4 in the last problem. So I push it, and I push it with enough force to make the velocity equal 1 meter per second. So with that in mind, let's look at the graph. How do we figure out what is? Now we're back to the position chart. Hold on. Now we're going to learn something cool. So the ball that we pushed, basically it's a constant velocity. So with this in mind, so let's sorry, the bar was up. So I may have said this before, I may have not, but look at this. We can figure out, oh, how far is a car going after 4 seconds? Let's do 4 meters per second times 4 seconds. When you cross off the units, you get 4 meters. Well, what is that called? You may be wondering. Well, that is called displacement. Displacement is the total distance traveled. So let's say Bob, the ball, traveled 3 feet forward. Then I pushed him 3 meters forward, sorry. Then I pushed him 3 meters backwards. With using the term displacement. Displacement is 0 because 3 plus -3 is 0. So basically what we're saying here is that we just proved displacement, which would be delta x, total distance traveled, that's displacement, equals the velocity times the time. Well, now we really analyzed the ball. Let's go back to it. Let's see what we know now, because we learned so many new stuff. See the ball on the ramp. Ignore this top part. I'm sorry. Let me just do. There we go. The ball on the ramp. Well, friction equals 0. Now we know for sure. Oh, let's go. Ball travels 5 feet. Using the displacement, delta x. It's moving at 1 meter per second. Oh no, let's change it up. The ball's moving at 2 meters per second now. So using displacement. Oh, what is it? This is all. This is a ball with 0 acceleration. So, as you can tell, I am proving Newton's first law, and I'm showing something with 0 acceleration, constant velocity. So this video is a mix of 0 acceleration, constant velocity. So, look at this. The ball, it's rolling. I push it at 2 meters per second velocity. So, and I know that, and travel 5 meters. So let's do some math. Total distance, so I don't know, delta x, so I'm just going to say x because I can't write delta on this keyboard, equals velocity times time. So now what? So x, we don't know. So we know the velocity. It is at 2 meters per second. Now we know the time. 5 meters. So let's do the math. So I just showed you. Look, it's travel. Sorry, not time. This is time. I'm sorry. I got this mixed up. Meters per second times 5 seconds. Now we do the math. S's, boom, they cross off because of units. Boop, cross off, go to units. So it's 2 meters times 5. Now that equals, boom, now you know the ball's at 10 meters. So using the applications of Newton's first law, I could show something with, a 0 acceleration. And I could show you what displacement is. Now, so basically, that is the whole summary of Newton's first law with 0 acceleration combined in. Actually, I was wrong. I'm sorry. But wait, there's more. Let's add. Let's go back to part of first law. What is net force? So this helps too to prove that there's no acceleration. So the first law really helps with 0 acceleration. Good instance. All right, so net force. What do you do? So basically, do you see these two lines right here? They're the same length, okay? So let's add vectors. How you add vectors, you connect them head to tail. So we're connecting them head to tail here. Whoa, look at that. There's no extra tail left over. So that shows there's nothing to connect the other head to tail with and make it a complete triangle. So that shows 0 net force. Let's say the triangle was like this. You need another line here, so that's net force. That means there is an acceleration. But since we're at this, that shows, oh no, look, 0 acceleration. And that's actually summing up all of 0 acceleration, Newton's first law. Newton's first law is amazingly and perfectly helps prove 0 acceleration with constant velocity. And this is Glenville, signing off.